Greetings to Doctor. We are from Group 2. Today we are going to present the mini project. The unit that I'm presenting is the oxidative reactor. So firstly, we have to form a enthalpy table and label all the unknown N. And given by the question, 250,000 MTA of AA is produced. Since the AA produced is 95% of AA feed, hence we can obtain the molar flow rate of AA feed by dividing with 0.95 and the molecular weight. And then by using the extent of reaction method for the AA balance, we can obtain extent 1, which is equals to N4. And then the question given the selectivity is equals to 16. So the desired product, which is the AA, divided by the undesired product, which is the ACA, we can obtain the N5. And then by using the extent of reaction method for ACA balance, we can obtain extent 2 followed by extent 3 because the question stated that extent 3 is half of extent 2. After finding all the extent 1, 2, and 3, we can find the propylene balance and H2O balance. So we can obtain N1 and N6 respectively. Next, question given that the percentage of excess of oxygen is 20%. So firstly, we have to find the O2 theoretical by using the extent of reaction. And then we can obtain the N theoretical of O2. We substitute this value into this formula and we can obtain the N2, which is the inlet oxygen. And then by using the extent of reaction method for the O2 balance, we can obtain the N7, which is the end outlet of oxygen. Then next for CO2 balance, the question did not give us the value of CO2, but we know that the inlet of CO2 of the reactor is equals to the end outlet of CO2 from the heater 1. So we can keep in view first. And then for the outlet of CO2, we form an equation by using the extent of reaction. And we link all the cells containing CO2 from the reactor to the heater 1, then back to the reactor. Then we will obtain the N3 followed by N8.
This is for oxidative reactor in inlet. There's two streamline, stream 1 and stream 5 in oxidative reactor. For stream 1, there is propylene, and for stream 5, there is CO2 and O2. To find the H for propylene, you can refer to table 3.2. So the temperature we use is 25 to 50. 25 is from reference state. So 50 is the temperature of current propylene. And then you just substitute the value into the formula given. And then for propylene, you will get 1651.9 kilojoule per mole. So for the rest, for CO2 and O2, it is the same. You can just use the table 3.2 to convert the value. And then for CO2, you will get 11,577 kilojoule per kmol. For O2, you will get 8,468 kilojoule per kmol.
The reactor, we have to calculate the enthalpy. So for this calculation, just use the sensible heat formula. For the temperature, we used from the reference state, which is 25 degrees Celsius until 300 degrees Celsius. So for the acrylic acid, the CPDT we can get from the data. So this is the data. Put in the formula and we get 21.39577 kg per mole. So for the other substance, just use the same formula and we get the answer. So this is for the acetic acid, H2O, oxygen, and carbon dioxide. And we have to calculate the NH, the N, and with the enthalpy. So we have to convert to from kg per hour to convert to kg per second, just to calculate the heat release, which is we get negative 90 854.92427 kilowatt. Okay, this is for my part. I will pass to the next person.
Good day, Dr. Hasmaliana, and also everyone. So for my part, I'll be explaining about the calculations for the enthalpy at the outlet of condenser. So the first substance that I'm going to calculate is acrylic acid at its reference state, which is gas form, 25 degrees Celsius and also 1 atmosphere. So, and then after that, it will undergo temperature increase until 141 degrees Celsius, which is the boiling point for acrylic acid. Then after that, it will undergo phase change from gas to liquid, and then undergo temperature drop from 141 degrees Celsius to 50 degrees Celsius, and finally, it will undergo pressure increase from 1 atmosphere to 2.57 atmosphere. So to calculate the enthalpy from the reference state to its final state, first we need to calculate the sensible heat from 25 degrees Celsius to 141 degrees Celsius. So to do that, we integrate the CPDT of the gas form of acrylic acid, which is 77.8028 kilojoule per kilomole, from 25 degrees Celsius to 141 degrees Celsius. And then you plus the heat of condensation of the acrylic acid. And then after that, you plus again the sensible heat from 141 degrees Celsius to 50 degrees Celsius. At this time, you integrate the liquid Cp dt of the liquid form of acrylic acid, which is 144.7 kilojoule per kilomole. And for pressure change, you plus 1.013 times 10 to the power of negative 4 times 72.0627, which is the molecular weight of acrylic acid, over 1.043, which is the specific gravity of acrylic acid, times 2.57 minus 1, which is the pressure difference. And in the end, you get negative 36,871.59 kilojoule per kilomole. The second substance will be acetic acid, and the way you calculate is similar to acrylic acid. There will be two sensible heat and also one phase change and one pressure change. Then so you just the temperature will be different, and also the CPDT will be different, and also the heat of condensation, molecular weight, and SG will be different. So in the end, you'll get negative 26,890.65 kilojoule per kilomole. For water will be same as acetic acid and acrylic acid. Will be two sensible heat, one phase change, and one pressure change. So in the end, you get negative 1,263.63 kilojoule per kilomole. For oxygen and carbon dioxide, it will also undergo temperature change and also pressure change, but we don't account for the enthalpy change due to pressure change. So we only calculate for the sensible heat. So what you do is you integrate the CPDT and from 25 degrees Celsius to 50 degrees Celsius, and then in the end, for oxygen, you get 738.14 kilojoule per kilomole. For carbon dioxide, you get 941.59 kilojoule per kilomole. That's all. Thanks.
This is a unit operation we pick, which is oxidation reactor and condenser. So for the calculation in Excel, we start with the basis value, which is 250,000. We calculate the mass flow rate by using the formula and link with the basis value we already keyed. We use this method to calculate for other molar flow rate and extent of reaction. For the heat of reaction, we calculated using heat of formation method. We already listed out the heat of formation for each substances. We make our calculation easier. And this is the formula we use to calculate the summation of heat of reaction. For the enthalpy table, we key in the molar flow rate we already calculated before, except for CO2. For CO2, we link it from the heater 1. And the H value, we already calculated it manually and type in manually. For NH, we times the N value and H value. And this is the unit conversion. And we sum up all the NH. And we done the same thing for the outlet. And for the Q out, which is the summation of heat of reaction, plus NH out minus NH in. So here is the mass flow rate, molar flow rate, and molar composition for each stream. For example, in stream 5, we obtain the molar flow rate from the enthalpy table just now, and we calculate the mass flow rate by timing the molar flow rate with the molecular weight. For the molar composition, we use the substance molar flow rate divided by the total molar flow rate. And this is how we do our Excel. Thank you.